In this section, 8.4, we're looking at 3 different areas for formulas for the area of a triangle. One of them you know from geometry, that the area of a triangle is 1/2 the base times the height. But you want to keep in mind that the base and the height have to be measured perpendicularly to each other. So if this is the base, then the height would be that length that I just drew in. But oftentimes what we're given is, instead of that information, we've got maybe 2 or 3 sides of the triangle and maybe one of the angles of the triangle. So we want to develop our formulas based on different information than just the base and the height. The first of those is, this is one of the new ones, that the area is 1/2 AB times the sine of theta. And the only requirement there is that you have 2 sides of the triangle. So let's say we have A and we have B, and then theta is that angle right there between the 2. So we don't need to know the height. If we just know those 2 sides and the angle between them, we can use this formula. We'll go through the proof of that formula. And then the third formula is good if we have 3 side lengths but none of the angles. So if we have sides A and B and C but we don't know any of the angles, then we can use what's called Heron's formula. The S in that formula is 1/2 of the perimeter, so you can think of it as like semi-perimeter, S for semi. We won't go through that proof because it relies on something that's actually covered in one of the sections that's coming up later. It's in 8.3. So that proof, I'm not worried that you know it, but be able to memorize and use that formula. I'm also not worried that you'll be able to prove this second formula, but it actually follows pretty easily from using 1/2 base times the height and some other things that we've done. So if we've got some triangle and we have 2 sides, let's put the A here and the B here, doesn't really matter, and then this angle theta. What we're going to notice is if we draw in what's called the height, we've got this 90-degree angle here, right? And the sine of that angle theta, if we look at this right triangle here, we can see that sine of theta should be the opposite, which would be h divided by the hypotenuse, which is b. And if we solve that for h, we've got h is the same thing as that side b times the sine of theta. So we can use our formula that says area is 1/2 times the base times the height. The base is A, and the height is B times sine theta. So that's where that formula is coming from, 1/2 AB times the sine of theta. So the only challenge is going to be assessing what information is given in the problem and then determining which of the formulas makes most sense to use. So here, example 1, we were asked to find the area and round to 2 decimal places, and what we have are all 3 side lengths. So whenever all 3 sides are given, we want to use Heron's formula. So if you go back and look at that formula, we have S, and then S minus A, S minus B, S minus C. So let's write down the formula. Square root of the semi-perimeter, and then 3 more factors, each subtracting one of the sides from the semi-perimeter. So S in this case is 1/2 of 4 plus 4 plus 3. 4 plus 4 plus 3, 8, 11 halves. So we'd have A is square root of 11 halves, and then 11 halves minus, let's call this, oops, no, let's see, A should be opposite angle A. This should be C, this should be B. S minus A, 11 halves minus 4, that would be 3 halves. S minus B, 11 halves minus 3, 3 is 6 halves, so 5 halves. And then S minus C is S minus 4, again, 11 halves minus 8 halves is 3 halves. So it looks like we've got 55 times 9 in the numerator and then 16 in the denominator. .495 over 16. So we want the square root of that. Get it? 495 over 16. 5.56 if we're rounding to 2 decimal places. All right. So, if given all 3 sides, Heron's formula. Next one, we've got 2 sides and the angle between them. So that means we want formula 2. That says area is 1/2 AB sine theta. It doesn't matter what's A and what's B. Conventionally, we would say, actually this would be called C. So it doesn't matter which 2 sides we have, A and B or C, whatever, but this is opposite angle A, this is opposite angle C, so really what we've got is a C sine theta, but as long as you've got any 2 sides and the angle between them, we have the right information. So 1/2 times 2 times 5 times sine of 20 degrees. So, turn it on, 0.5 times 2 times 5 times the sine of 20. .71. And I guess we should be putting labels on these square units. Same as the last one, since we're talking about area. So you can either write square units or units squared, either way is fine. A couple more examples. Instead of being given a picture, if we're given this information, side B is 4, side C is 1, and angle A is 120 degrees. 120, that's an obtuse angle. B is 4, C is 1. This is going to be the short side. This is going to be the long side, so I'll call this one. And then A is over here. We don't know A, but that's all right. We have the information with 2 sides and the angle between them. So we'd say area is 1/2 of one of the sides times the other side times the sine of the angle between them. So 1/2 times 4 times 1 times sine of 120 degrees. Half of 4, that's 2, times the sine of 120 degrees. 1.73 to the nearest tenth. Let's think about this. Sine of 120, we should know that one. So we could get, that's approximate what we just wrote down, but this one we should be able to get exactly. 120 degrees. That's 60 degrees short of 180. So we could use this 60 degrees over here. It lands us up a little higher than what I've got. Draw that a little better. So 120, that's 60, this point would be 1/2 square root of 3 over 2. So over here we'd have negative 1/2 square root of 3 over 2. So the sine value is square root of 3 over 2. So we could get this one exactly. So we'd have 1/2 times 4 times 1 times square root of 3 over 2, which is just going to give us square root of 3 units squared. So the approximate value would be 1.73, but since they didn't ask us to approximate, and since we can find that value exactly, it's better to leave it as square root of 3.
In example 4, here we're asked to find the area of the shaded region, which here is a little bit tricky to see, but it's this part right here that's outside of the triangle but inside the circular sector. So we want to be thinking sector area minus triangle area. For the circular sector, we want to use 1/2 r squared theta. But in that case, if we're using that formula, theta is in radians. So we'll need to convert that angle to degrees. Excuse me, from degrees to radians. And then the triangle area is 1/2 AB sine theta. And for that formula, since we're taking the trig function of the angle, it doesn't matter whether the angle's in degrees or in radians. We would just want to make sure we have the calculator in the right mode when we compute it. Just to make things easier, let's switch these both so that the angle's in radians. So 70 degrees times pi over 180. So that's 7 pi over 18 if we reduce it. So now we've got 1/2. The radius is 8. So 8 squared times 7 pi over 18 minus 1/2 times A times B. A and B would both be 8, the two sides of that angle at 70 degrees. So we'd have 1/2 times 8 again, times sine of 7 pi over 18. So that would be the exact, so half of 64, that would be 32 times 7 pi over 18 minus 32 times sine 7 pi over 18. We can grab a calculator any time here and evaluate that. We could do, factor out a 32, but let's get a calculator because we're going to want an approximation anyway. That's not a very nice value. So 32 times 7 pi over 18 minus 32 times sine of 7 pi over 18. I'm going to check the mode. It's in radians, and that's good because the angle's in radians, so about 9.03. And let's see, these were in just no label, so we would say 9.03 square units.